Just a quick check again, audio check. I think you can hear me, isn't it? Should be fine. I can see my microphone working. Now, this is just a quick announcement for those of you who are looking for internship. I think this has been sent to maybe all of you, but just again, just a reminder in case you have not seen it. Now, this is this is the company in Kuala Lumpur looking for basically. I think don't worry about whether it's mechanical or mechatronics or even E&E. If you think that you meet the requirements, because I look at it, it's quite simple. Looking at the engineering background, able to develop database and use Excel, right? And then the third one is actually a program called Sketch 3D. I think 3D design. I think for us we use the SolidWorks, right? So maybe we can also and then experience in the CAD design, CAD drawings, maybe not E&E, but mechatronics. I think you should be able to do some CAD drawings. And then I think the last one, Google Slides or PowerPoint, I think the one you've been well trained. I think I checked the website, the pay is about less than 1,000. So if you're interested, please apply. So it's down there, the QR code as well as a link. Okay. So I think I'll move on. After this, I'll move on to the other lecture. Any questions from the previous lecture? Okay, now this one actually, as I promised you, this is the one I talked about, I think the last week, talking about basically an AI solution to monitor the dropping of the fruits of the durians, right? So this one is actually a picture taken from the newspaper. So you can see actually this is the durian farmer. Okay, just to share with you. Now this one's actually basically you look at it, the problem statement. I think this is also can be a very good example case study for entrepreneurship. Of course, in the industry, the first thing to ask you is why do I need to pay extra, right? So the problem statement is that this durian farmer, Chang Tek Singh, he and his family needs to find the fruits as soon as they fall, and that must be between 20 minutes and 120 minutes, basically 2 hours, less than 2 hours. So they want to find, right? So that is a problem they need to solve. So why do they need to find the fruits, fresh fruits as soon as they fall? Because why? Such fruits fetch a premium price. That means a higher price. Again, if you look at the problem itself, right? I think we reflect back on your entrepreneurship. In the world of a high competition, everyone is selling durians in Penang. So how can I sell better? How can I stand out among all the other durian farmers? So the answer is because if you can sell those fruits which are freshly fallen, because they provide extra sensation, which is a tingling sensation, a numbing sensation when freshly eaten, freshly defined as less than 2 hours. Now, the other problem is that, yes, it's a simple problem, don't need AI solutions, but I have a large plantation. I have a large plantation and I've got 200 durian trees, right? And it's a hilly area, 6 acres. So you can see it's a hilly area on the slopes or the hills, not easy to find. And so it takes a lot of time to look for a fallen durian from every tree, right? 200 trees, how can you find the durians? Even though the durians may not be fallen onto the ground. I understand that nowadays they put a fishing net underneath the tree so that the durian will not fall onto the ground. So we can still see them and then the durians will not be injured. Right? Now, what is 6 acres? 6 acres is a very large. How big is 6 acres? 6 acres, I'm giving some example, is actually equivalent to 96 tennis courts. So it's a large area. So imagine you have to look for those durians in such a large area as soon as possible. Right? I don't want you to go all over the place. So if you know where the durian has fallen, exactly where is it, so you can quickly go to the exact location rather than wasting time looking at other places. And also, since it's hilly, it can be quite tiring. Right? So the proposed solution will be, first of all, they need to set up fish nets to catch the fallen durians. So that, as I said before, you don't fall onto the ground, so your durians will not be damaged. And the other thing is that they put the sensors on each of the trees, the tree nets, to detect the change in the net tension and the weight. So that when the durians fall, right, and no durians, so the tension is different and the weight of the net itself is different. So that is actually sensors. And again, this is obvious solution. Now, using 5G, there's a change in your net tension. So again, you need to reset. You need to know what is the net tension without durian fruits and also net tension up with durian fruits. So actually, what we call abnormal state detection. So that what is normal? Normal is there's no durian. So there must be a setting, right? Now, question is this AI? It seems straightforward, right? I can just check for the tension, right? And the weight, and then of course connect to 5G. 5G is actually just nothing more than just basically transmitting the data back to your processing center, right? So AI actually here. Now this is application of AI. Why do we say that? Look at it. It's a practical. It's a real problem that is actually well defined. It combines the latest technology of AI and 5G. So there's a simple yet effective solution. Basically, it checks for the change of tension of the weight. And of course, it must be low cost with a high accuracy and precision. So these are the things that your customers, your users want. It must be accurate, right? Imagine if your system is not accurate, right? So I give you false errors, right? I can foresee if it seems simple enough, you put a net there and then you check for the tension. But what happens if a bird sits onto the net, right? A squirrel sits onto the net. Animals are small animals. So I think there's also this kind of things you need to take care of. So to me, that sounds like there's some AI involved, right? To actually, so that you do not get a lot of false errors due to the squirrel sitting onto your net or maybe a bird sitting on your net, right? So this is actually a form of AI. So this is just to share with you how AI has been used and is combined with other technologies, which is your 5G, right? This is where we stopped the last week, isn't it? Right. So before I forget, don't forget there's a replacement class tomorrow, 2 hours, 9 to 11. So please join us tomorrow morning. So again, as usual, before I continue the rest of the lecture, are there any questions on the previous lecture? That is on the knowledge and then the setup, who are the main team members of your expert system development team. Remember, we have this the project manager, the expert talk to, the knowledge engineer, right, and the programmer, and finally your user. Okay, any questions? Any questions you want to ask? Let me check. You guys are very shy. I need to check your chat box. See any questions? Okay. If not, we will now quickly in the next say 40 minutes, and then start a new topic. Thank you, Jing Yong. So far, so good. I think I can see actually if you just pay attention, it's not that difficult to follow this particular paper. The rest of the topics, of course, if you have questions, of course, I'm most happy to answer. So now look at the various methods to process the information in your expert system. One of them is forward chaining. Now, what is forward chaining? Oops, sorry, before I forget, I made the mistake again. Luckily, this time I remember. Otherwise, I'll be talking for 1 hour. Sorry, because I think you guys wanted the recording. I can forget. Let me start the recording again. This call is now being recorded. Okay, now the expert system, how do you process the information, the data, plus the rules in your expert system? So there are two methods that is commonly used. One of them we'll study here, and then later on we go into the second method. The first method is known as forward chaining. Now, what is forward chaining? Forward chaining is a data-driven reasoning, right? Because you have your data, you have your rules. So you need to make sense of your data based on the rules. The rules capture the knowledge. It's something that we talk about in great details in the previous section of this lecture. So you have the data and you have the rules. So you need to make sense of the data that you have based on that knowledge or based on these rules, which are extracted from the experts. In this case, it's a data-driven reasoning. Based on the data, I'll tell you this is what I think it is. So this is data-driven reasoning. The reasoning starts from the known data. So your data that you collected from the census. Now we go back to the example of the durian farmer and his 5G and AI solution. So based on the data collected from, they say, the fish nets, what does it tell you? And then from there, it will process the data, and then from there give you any 5 of those. Remember the 5 possible output of your expert system. Right? It is a recommendation, it's a suggestion, it's a directive. Remember those things? So those are the things we output from this expert system, from this forward chaining. Now, what other thing must you know? You have a set of rules. Now, again, no matter what you do, the rules will be arranged in a certain order. Right? So no matter what we do, we know that the rules are, even though you may not like it, the rules cannot be all at the same level. So even at the same level, it will be, say, left to right or right to left, right? So there were some rules which will be processed or executed first. So in this case, assume the rules are arranged in the vertical order. So each time, the topmost rule will be executed first. So you process the first rule in your knowledge base, the topmost, and then you go down. Right? You look at the first rule. So that's what you mean by processing it. Look at the first rule, and then we look at the rule. Does the rule satisfy? Are the conditions for the rule satisfied based on the input to that rule? So if that rule is satisfied, right, then it will be fired. It will be executed. It will be processed. Right, it will be fired, and the rule then, as a result, adds a new fact to your database. That means that rule is fired, and then of course you keep note of that rule which has been fired, right? So second thing is that you do not need to execute the rule more than once, meaning that all the rules can only be executed only once. You do not need to go back and reprocess it again, which is similar to your search again, right? Remember, if you want to find the sequence of towns you need to visit, you don't go back to the one you visited before. So as long as you process already, you don't need to go back. So only thing same with the rules here. The rules in the knowledge base can only be executed only once. This is what we call the match fire cycle. You look at the rules. Does it match your inputs? Yes, you fire. Otherwise, you skip. You go to the next rule, right? So this match fire cycle stops when no further rules can be fired. Of course, it is clear that you need to go through all the rules, and then some that fire, some may not fire. So again, you need to process all the rules, right? No rules can be missed. Otherwise, your system will not be accurate. So now we look at some of the rules here. For example, we have this example where we have a set of 5 rules. So we rewrite the rules and then add 2 rules. Let me see here. Okay, this is what we have. So we have, this is actually based on the, I think, earlier example. So now we have a total of 5 rules. So we have 5 rules here. Let me check. Okay, this was actually based on the, I think I might miss this. Okay, this is the one I missed out. That's why it makes a bit strange. It's the one. So it's the one here. I think the one we actually need to revisit again, because otherwise you miss out. Okay. Now, as I said before, there are 2 methods for reason, right, in the rule-based expert system. So as I said before, the domain knowledge is represented by a set of if-then production rules. That's how we not represent the knowledge. So this will be the form of if-then. Of course, there can be more than one set of conditions. That's why you use either and or the or functions. And the data is represented by a set of facts. So these are the data from the input data from your sensors or other types of sensors or other types of devices to collect the input data. So this one will give you the real-time information about the current situation. And then the inference engine, right? So this is your inference engine, will then compare each rule stored in the knowledge base, right? So that's how you process the rules in your knowledge base with the facts contained in your database. When the if condition part of the rule matches a fact, the rule is then fired. I think this is something we discussed before, so I'm just revisiting this. Then this is what you call firing. So it's fired, and then the then action part is executed. So if the input condition matches the if part, the antecedent part, so the consequent part will then be fired. If not, of course, the consequent part will not be fired or will not be executed. Now, this matching, so you can see, actually matches. You try to match the input conditions with the rules that you have, right? So, because your rules will say, I think we talked about this before in one of the early examples. If you are a banker and this person comes to see you, then you say, I want to withdraw money. So first of all, what do? We say that, what's your age? If you're above 18 years old, you can then withdraw any amount you want. But if you're less than, say, 18 years old, if you want to withdraw more than 1,000 ringgit, I need your guardian's or parents' signature. You can only withdraw less than 1,000 ringgit. So those are the matching of the rules. So the matching of the rules of the if parts to the facts, right? So for example, in the earlier example, talk about the young person coming to the bank. So what's your age? So that is your information, that's your fact, that's your input. Then you look at the rules. If your age is less than 18, right? Then I need your parent signature. If your age is less than 18, no need, you can withdraw. You can withdraw up to 999 ringgit and 99 cents because it's less than 1,000. Anything more than 1,000, I need your parents or guardian signature. So this is then it produces what we call inference chain. So each rule will produce an inference chain. That is by matching of the rules that fire. Now, it is this inference chain that indicate how an expert system applies the rules to reach a conclusion. So there's a series of inference chains as you see later on, right? This is where we sort of stopped last time. So now we talk about, okay, right, then have this. So we can see here, this is your basically your visualization, representation of the inference engine matching, right? So you have a database and your knowledge base. So basically, you can see here, the database is actually your input, right? It matches the input A, so the age of the young person, and then match to the rules. So this is your knowledge base, which was, remember, is extracted from talking to an expert. So these rules are not randomly generated. They must be generated based on the expert's knowledge. Then if the fact is matched, so if A is actually X, then this rule will fire. And then when it fires, you assign a value of Y to B. It's fired. So you can see it's one way, right? This is so this one actually, this is your output of that. So this is a visualization or graphical representation of your inference engine. So now this is the one we talk about the file. Find a bit. So initially we have three rules. So we have three rules here, which we talk about. If Y is true, so this is the rule number 1, 2, 3 actually goes in back here. So we have three rules here. So if Y is true, then D is true, Z is true. But what happens if X is true, right? So another rule is that if X is true now, so you can see here, I actually have three inputs. But X is true, then B is true, and E is true. So you have X is true, B is true, E is true, then Y is true. But this one, Y only contributes to Z, right? So this one, actually you can see here, this rule number 2 will influence, will affect Y. So Y is not actually, it's not from the sensor, it's actually as a result of your rule number 2, which will only fire if X, B, and E is fired. Now finally, you can see here, if A is true, right, then X is true. So again, in this rule number 2, X is actually not your, actually dependent, it's actually depend on your rule number 3, which is actually A. So only if A is fired, right, and X is fired, then X will be fired. And then combine with B, that will then fire Y. Of course, you have to wait for D before you get Z. So this is where we were of the three rules. That's why we have this. So now we add two more rules, which is rule number 4 and rule number 5, which is if C is true, then L is true, right? This is what we call shorthand for writing the rules. Actually, can see we miss out. We don't need to show the if and the then part. So the then part is represented by an arrow. So if C is true, then L is true. Then the next one, rule number 5. These are the two new rules. If L is true and M is true, then N is true. Oh, here. So these are the. Now, how does it work? So this is the visualization of the two parts. Remember the two parts we showed before early on? We have your database at the top here, and then the bottom here is your knowledge base. Right. What else do you see? These two blocks here represent the first cycle. The first cycle, and then the next one, this block here, number 3, or this third column represents cycle 2, and the final one represents cycle 3. Let's look at how this works, right? Let's look at the first case here. Now, in the cycle 1, this is cycle 1, right? You have two rules. Okay. Rule number 3 here, this is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So let's see whether I can show this or not. Or I come back to this. Okay, this is a visualization. So we go back. If in the cycle 1, let's see, go back here. This one is, let me see, if I go back. Okay, I'll go back here. Okay, now let's describe this cycle one. So in your cycle one, only two rules, rule 3 and rule 4, matches the facts in your database, because this is your database. Explain. This is your database consisting of A, B, C, D, E, X. What does it mean? It means that these are your information, these are the inputs that you see, either from the sensors or something else, right? So you have basically this database consisting of these inputs, A, B, C, D, E, is true. So if you look at A, B, C, D, E, you look at the rules. First one, Y, and if Y is true and D is true, then Z is true. So do I see Y? Do I see D? I see only D, I don't see Y. So this one, it does not fire. Right? So again, a footnote here, X is actually not there yet, because as I said, so A, B, C, D, X is actually the result of rule number 3 firing. So initially, X is not there. So you only have A, B, C, D, E. So you have A, B, C, D, E. So first rule, I need Y and I need D to be true. I can see D, I don't see Y. So first rule is not fired, not match, will not be executed. Then what do? You skip that and go to the next one. The next rule will be X. If X is true and B is true and E is true, then Y is true. So do I have X? Right? As I said initially, X is not there. So you have only A, B, C, D, E. So I have B is fired, correct? E is true, correct, but I don't have X. So does rule number 2 fire? No, correct? So number 2 again is not fired, it's not executed because it is not fulfilled. X is missing. Rule number 3, A is true, then X is true. So I have straightforward, I can see A is there. So therefore, rule number 3 will be fired, right? So you have rule number 3, and then next one. So after this is fired, then you put X over here in the database now. The next one will be if C is true, then L is true. Do I see anything? Do I see C, right? I can see it. So therefore, L will be fired and L will be added to my database. So you can see here, this is your second part. So once rule number 4 is fired, you add the output L into your database. And the last one, L and M is true, then N is true. Do I see L? Do I see M? So this will be here, right? After rule number 4 is fired, it's executed. So do I see L and M? I see L, but I don't see M. So rule number 5 will not be fired. That's why here you can see that you only have a rule 3 and rule B fired or executed because they match the facts in your database, right? So again, you can also see clearly it's also very dependent on the order of your rules, right? Imagine if you have put now we put rule number 2 on top of rule number 3 on top of rule number 2. So you see, if we say the rule number 3 is here, you swap place. So if A is true, X is true. Then if we put rule 3 as rule 2, then this one will be fired. You see, so again, it's a very I think the system itself will be sensitive to the order of your rules. But so happens in this case, rule number 3 is put after rule number 2. Therefore, rule number 2 will not be fired. Clear? So going on to the next point here, rule number 3. Now A with X is fired first as the topmost one. So I think we explained this before. So this is then I think this basically explains it. And I think now I'll move on to the visualization of how this is done. Okay. So this is what happens. So you have, I think this is, I think I've explained that, but this one gives you a visualization how it actually works. So you have rule number 1, you look at check rule number 1. I call this cycle 1.1, and then nothing happens. So you have rule number 2, nothing happens, and then rule number 3, that's where you fire it, and you can see you put X now into the database. Then you have 1.4 going to the fourth rule, and then you have it, and then you fire it matches, and then therefore you put the output L into the database. And finally, your last rule, nothing happens, so you go back. So this completes your cycle number one. So you can clearly see that cycle. Each cycle will have to process all the rules that are in your knowledge base. This is a knowledge base and the database. You can clearly see again they are separated. Now, after you finish your cycle one, then you have to look at your cycle two. Because why? Because you can see the database has changed from the previous cycle. So therefore, you can see that because of this change in your database, so your processing is not complete. So basically, what it's saying is that you only stop when you see your input database has not changed. So in the cycle number two, then we look for rule number one. Right, rule number one, y and d is true, then z is true. Do I see y? No, I don't see y. Yeah, y is only there after rule number two is executed. So in this case, you can see that. Let's go back. You can see that in this case, y and d is true, z is true. So you can see if I process this rule here, I can only see d. I don't see y. Right? I don't see y being true. So that's why rule number one is not fired. Now, rule number two now. If X is true and B is true and E is true, then Y is fired because your facts, your inputs, B, E, and X are there, already in your database. So therefore, it's fired, and as a result, your fact Y is inferred is true, and therefore the output Y will be put inside or introduced into your database. So you have A, B, C, D, E, X, L, Y as a result of that. Okay. Now, so you can also see that the colors, what do the colors represent? The colors represent that these are the rules that have been processed, matched, and you do not need to go back again to these rules. So you can see I only look for the rules which are in white. So after rule number two, I will jump straight to rule number five, which is L and M. Do I see L and M over here in my database? I don't see. So therefore, in cycle number two, my rule will not be fired. Now, do I need to go into cycle number three? Yes. Why? Because my database has changed. So now I have a new input called Y. So therefore, I need to process again until my database stabilizes or does not change. Yes? Follow? Now, so now I go into cycle number three. Right? So cycle number three will be I look for Y and D. Right? So I look for Y and D. I can see that since rule number one, rule number five are not processed yet, I process the first rule, which is if Y is true and D is true, then my Z is true. So I look for, do I see Y? Yes, it's here. Do I see D? D is here. Therefore, this rule will be fired, and consequently, the Z will be introduced into the database. Now, this matching and matching firing cycle will stop because, okay. So the next one will be Z is introduced, and then I have, of course, I jump to the fifth rule, L and M. Do I see L? Yes, I see L. Do I see M? Is M fired? Right? Is M there? Right? Is M true? So I don't see M here, so I assume that M is not true. So this rule will not be fired. Right? So then I jump back to my next cycle, right? Because my Z has been just introduced into my database. So my database is no longer the same as before. I have now 9 values. Previously, it's only 8 values. Now I have 9 values. So it has changed. So I will then go back and look at it one more round. So then I look at then I process. Now, only rule left, which is actually left for me to process, is actually rule number 5. I process all these rules, so therefore, as I said before, we do not need to process them more than once. So look at the last rule, L and M. If L is true and M is true, then N is true. Do I see L? Yes, I see L. Do I see M? I don't have M. So therefore, this rule will not be fired. So therefore, I stop because the database has not changed after this, right? So this stop because rule number 5 does not match all the facts in the database, and therefore rule number 5 cannot be fired. So it's when you stop. So I've only fired 4 rules, and I got these 4 new inputs as a result of these 4 rules being fired. Now, what is the forward chaining? So I can see clearly that forward chaining is a technique for gathering information. I get the inputs. As a result of the inputs, I can now get new information, getting information, and then based on that information, I will infer whatever can be inferred from it. I will then infer from it whatever I can infer from those information. Now, however, in forward chaining, you can clearly see that many rules may be executed that have nothing to do with the established goal. Right? I think later on you'll see what we mean by that. So therefore, if let's say our goal is to infer only one particular fact, the forward chaining technique can be seen to be inefficient. Like let's say, if I just only want to see when is it Z is true, right? You can see that if I only care about what is when Z is true, I have to process whether Y is true, I have to process whether X is true, I have to process whether L is true. So that is a wasting of my processing power. I need to process all this in order just to find Z. So let's look at it further in the next few slides, and that may become clearer. So that is the forward chaining. Now let's look at the backward chaining. Now forward chaining is data driven. I can see here. Backward chaining is goal driven now, based on the goal, the objective. Now what do you mean by backward chaining? So in backward chaining, the expert system has a goal, what you want to do, right? There's objective, a hypothetical solution. So this is actually at the start, it will be hypothetical. It's a goal. And therefore, your inference engine will attempt to find the evidence to prove it. So you say that this is true. I want to find the justification to support my theory that this is true, right? As you'll see later on. So your inference engine will try to find the evidence to justify, to prove it that this is indeed true, right? Your hypothetical solution, right? Good example would be say my car cannot start. I suspect it is due to the battery being flat, right? So I will try to find the information to support that the engine cannot start because it's due to the battery being flat. So the first thing is your knowledge base. The if-then rules, it will be searched to find the rules that might have the desired solution that contribute towards your hypothetical solution. Such rules must have the goal in their then part or the consequent or action part, right? Then or action or consequent parts. So they must have the goal. So you look for those that have that goal in your action part. Now, if such a rule is found, so again, you have to search, again, searching all the rules to find such a rule that has this goal in the consequent part or the action part. And then it's if the if part or the condition part or the antecedent part matches the data in the database, then the rule is fired and the goal is proved. So you have to, so it's actually working backwards now. You look for the then part for that goal. If such a rule is found and the if part matches the data, so you have to look for the then part and look for the if part now. Does it match the data in your database? If yes, then the rule is fired and then you prove your goal is correct. However, unfortunately, this is rarely the case. So therefore, your inference engine puts aside the rule it's working on, with the rule is set to stack, so that if that rule is correct, you put it aside first and stack it up and set up a new goal or sub goal, so to speak, to prove the if part of this rule. Then the knowledge base is just again for rules that can prove the sub goal. So you have your main goal and then you have a sub goal. You stack it up, right? And then you go back, right? Then the sub goal, the knowledge base again search. So you search your knowledge base for rules that can prove the sub goal. Now the inference engine will repeat the process of stacking the rules until new rules are found in the knowledge base to prove the current sub goal. So you have to look for the knowledge base, search for knowledge base, and then until no rules are found, then when no rules are found, you stop. It's when you stop. The knowledge base will be searched for you to prove the current sub goal. So first of all, you have the main goal, and then from there you created a lot of sub goals. This is the, let me see. Okay, this is the visualization of your backward chaining process. Okay, let's look at it one by one. So the first pass of your goal, I want to find out, my goal is to prove that Z is true. So therefore, my inference engine will then find the rules from the knowledge base to show that, look for the fact Z, and searches this knowledge base to find the rule that is this goal. First, Z is my goal. So I will have to find the rules that have Z as the goal in the then part. So once the inference engine finds that particular rule, and then it will then what we call stack the rule number one. It will put it aside, right? In this case, you can find that I'm looking for only the then part for Z. So you can see here, one by one, I look for it. So I see this one. I will then find it and put it aside. So in this example, your if part of the rule, so once you have this this rule found, you will then look at the facts. Now I will look for Y and D. So these facts must be also established. So because of your rule number one, which has Z as the output, I will now look for this rule will be stacked because it's actually true, but then I'll look for your Y and D. So these rules must be Y and D must be true first, right? So after I found Z, I must prove the Y and D exist in order to support my rule number one. So in the second pass, right, now I have this Y, right? So Y now, Y and D, D is there, so only thing left is Y. So the inference engine will then because Y is not here, so this will be my sub goal. This is a Y, is Y true, and tries to determine it. First, it checks the database, right? Database and for Y. Okay, of course you also know that I will check for both Y and D, but I can only see D, I cannot see Y, so I will look for Y. Then the knowledge base is search again since I cannot find Y, I will look for the rule with Y in its then part. Of course, you can also see that if it happens that Y is there, of course, you don't need to search. Then you say that it's proven, it's proof that Z is true. But in this case, I can only see D, I cannot see Y. So therefore, I will now have Y as my sub goal. So then, of course, again, the same thing applies. You cannot process the rules that has been checked before. So that's why you skip rule number one, you go for number two. So then, of course, you're looking for the Y part, which is a sub goal. So do you see why that in the sub goal? That rule number two consists of the facts or inputs X, B, and E. So of course, again, in the same process as before, you have to prove that or justify that X is true, B is true, and E is true. Do I see that here? In my database, I don't see it, right? I will put it aside and then I will find the facts, so I will now have X as my sub goal now to find the rule that has X as the action part or the consequent part. So I go to pass number 3, the third round, third cycle. So in this case, in the third cycle, I have now set up the new sub goal as X. So your inference engine will then set up fact X as your new sub goal. It will check your database because I have B and E. Of course, it's understood that B and E you also need to check, but B and E can clearly see except for X. So X is not there, so you check your database for fact X, and when that fails, searches, assuming it fails, I can see it fails, it's not there. So therefore, I will find out the rule with X as my sub goal. Now, then I find that in my rule number 3 now. So 1, 2 is actually processed already, put aside. So you have only 3, 4, 5 rules to check. So I'll check for the rule that has X as my action part or the then part. So I find it in my rule number 3 here. So I find it in 3, therefore I must also now for rule number 3 to be active, right, to be true, I need to find the fact A. I see in the rest. So in this fourth cycle or pass, I can see that A is there in my database. So the engine finds the fact A in the database, and then as a result, X, this rule number 3 is fired, and the new fact X is inferred. So if this is true, this rule number 3 is true, it will then be fired or executed, and X can now be added to my database. You can see here. So the first pass, therefore, the inference engine now returns to the sub-goal fact. So I don't need to check the rest of the rules anymore. I need to check those which has been stacked before. So now I'll go back to my first one, which I stacked, and sub-fact Y. And once again, try to execute rule number 2, which is XBE to give me Y. Right, because rule number 1, which actually you put aside early on, has been there, but again cannot be fired yet because your Y is missing. So you check number 2, which has been stacked before, and then you see, yes, in this case, rule number 2, facts X, B, and E are in the database, therefore rule 2 is fired. So after you finish the first pass through all the main rules, then you go back to your sub rules, to your stack rules that you 3 of them stacked before. And therefore rule number 2 is fired, and a new fact X is then executed and added to your database. Right, so you have your rule number 2, which actually stacked before fired. Right, so you can see here, you can see the color here has changed. The rules that are fired, that can be fired or matched, are actually colored in light blue. What do you do next? Number 6, pass number 6. I do not go back to these rules here, the one in white, but go back to the one which I actually put aside as which I stacked before. So there's only one left, which is right, this one, the first one, Y and D. So the system now returns back to your stack rule, which is rule number 1, and try to establish the original fact, which you're trying to find, which is Z true. So you can see Z is only true if Y is true and D is true. So you have your D, and then Y has been just recently added because of rule number 2 being fired. So therefore, the first rule now will have all the facts in my database. You have your Y and your D. So therefore, the original goal, the original aim of your reasoning, which is goal-driven, which is the backward chaining, is now finally established. You finally get your Z. Right. What else can you see? You can see here visually in my picture here, the goal is Z, and I do not need to process the other 2 rules, which is my rule 4 and rule 5. Right. So this is you can see actually is much more efficient, but it's actually based on, but it's only for backward chaining. You have the fact, you have the goal, and you just want to prove the goal. This is what you do. Unlike the earlier one, which is data driven, this is goal driven. based on the action part, you try to prove the action part is true. Whereas the forward chaining is based on the inputs, and then you try to find what is the output based on those inputs. So it's now this is actually, you can clearly see now if the rules are actually in the real system, a few hundred or few thousand rules, this can be very fast, much faster than your data-driven forward chaining system, inference engine. So when do you use forward chaining? When do you use backward chaining? If the expert means that the humans needs to gather some information and then tries to infer from it. Whatever can be inferred, you choose your forward chaining inference method or inference engine. If you need to find, you able to gather some information, right? If you can gather some information, and then from there, I get the information that the sky is blue, or maybe not the example. Maybe the sky is blue, means no clouds. It's very bright. It's sunny. It's hot, and then the weather forecast says it's going to be sunny. What should I do? Those are your facts, and then from there the consequence, which is the then part. So this is you use your forward chaining. However, if your experts begin with a hypothetical solution, I think today it will not rain. That is my conclusion, my then part. I will then try to find the facts to prove it. So you're working backwards now, right? So if you're working backwards, clearly you use your backward chaining inference engine. So that this one, I think, will give you some idea when do you use your forward chaining and when do you use your backward chaining inference engine. So that is a part on the backward chaining and your forward chaining. Now we move on to another part of this expert system, which is conflict resolution. Am I going too fast, or can you all still follow?
Follow.
Good, thank you. Now, if you disagree with your friend, please don't be shy. That's why if you're shy and you lose, so you find that you cannot follow or need to go back to a certain parts, please let me know. I'm most happy to go back to explain to you again. Jin Yong, yeah, okay, but I'm not sure about for the other 88 students, whether they can still follow.
Sir, because this sounds
wait. Yes, go on.
Oh no, this sounds like a bit like normal if else, at least the previous one lah. The backward one is a bit different, but the forward chaining kind of sounds like normal is if else only, isn't it?
Yunzi, you are absolutely correct. This one is actually based on what? Human experts, isn't it? The way we reason. So in a way, it's very normal. You're absolutely right. So it's actually, you can see, I think you're surprised, isn't it? What am I learning this? Isn't this very normal?
Yeah,
You're right.
I was surprised.
You're
So,
right. You're right.
In a sense, the fuzzy logic is like applied if else only, right?
Wait. Fuzzy is next week. Next week, coming soon.
Oh, I see.
It's
But
again
this is
similar.
base, is it?
This is based on expert system. This one you see the difference between the fuzzy and your expert system. And I think going back to Yun Si's question, the forward chaining is very obvious. If I see this and I see this, this is my conclusion. Okay, let's give it a simple example. If I see that I go to the class, Google, this kind of Google Meet, Google class, I find that there are no students there, 0 students, right? And I know the time is correct. Then I conclude that, is it correct? Then I find that maybe there's a holiday. So I think today's a holiday. I'm trying to prove that today's a holiday. So I'm working backwards. So I find the facts to support the decision that today's holiday. Therefore, the facts is, if today's a holiday, the then part, there will be no students, and what's the other one? I think only no students are. So students will not turn up for class. So in that sense, it's working backwards. Fuzzy, just to give you a little bit of extra information, because you can see, okay, go back to our example. If I have the sky is blue, no clouds. If the weather forecast is sunny, what's the third one? One more, isn't it? Sky is sunny, weather forecast is there, and the weather forecast. Okay, let's say two. Weather forecast is sunny. The sky is blue. Therefore, I don't need to. I think it's going to be. I don't need to bring umbrella, right? You can see what is that? Is it 100% or is it 99? Or is it 70% that I'm correct? Yes, you see already. I think you see the plane. It's 100%, isn't it? It's not probable. It's actually, if the sky is sunny and the weather forecast from the radio or TV says it's not going to rain, that means that it's 100% that it will not. I don't need to bring umbrella. But fuzzy is different. Fuzzy, it will give you a certain percentage. That's what you see. It's a whole new area. So, but fuzzy is right. Fuzzy is closely related to expert system, as you see later on. Unlike your neural networks or even your particle swarm, well, not particle, swarm intelligence, as you see later on. Okay, so a very good question, because it actually first of all say that this is like Yunxi's first statement, very normal, very obvious, common sense. Why am I learning this? But it's actually that, because that's how we humans reason. If I see this and see this, then I say this is my conclusion, right? But again, if you know, all of us know, somewhere along the way, sometimes we can be wrong. Our rules are not perfect, and so you need to tweak the rules, right? So good question, thank you. So
Okay,
let's continue.
Thank you, sir.
Welcome. Let's continue. Where are we? Conflict resolution. So this is a new part here. It's a new part. Why? Now let's look at the two rules. Two simple rules now. And first two rules. Let's say this one is not there yet. So the first rules, let me repeat. If a traffic light is green, then you go. Traffic light is red, then you stop. Right? Those are two rules for how you cross the road. Now let us look at the include a new rule now. Somehow we generated a new rule. So this new rule, this example, don't ask me the logic behind that. Maybe the programmer or the knowledge engineer somehow put in the wrong rule, right? If the traffic light is red, you still go, right? So what do you see here, right? We see here, if I process these two rules, I should stop if traffic light is red. Now, if I were to process the third rule here, I go. So what happens? As a human, we know that this is actually not right. So, but in terms of a mechanical system that follows these three rules, what do you think it will do? It will be confused, because this rule is not right. That's what we call conflict. It's conflicting against the earlier two rules, because traffic light is red, you go. I can put another rule inside. Rule number 4. If traffic light is green, action is stop. Right? Can see actually it's a wrong, but it's a conflict. This is very obvious, but in some cases may not be so obvious, right? As you see later on. So we have two rules here, number 2 and number 3. Rule number 2 and rule number 3, with the same if parts, 2 and 3, right? Same if parts. If the traffic light is red, both of them have the same if part, but the consequent part is different. So therefore, both of them can be set to fire when the condition part is satisfied. That is, if you see the traffic light red, both of these will fire. But but these rules represent a conflict set. It goes against each other. Right? It's not supporting. If I use the word supporting, it's not supporting the earlier rule, which is it's not supporting, say, rule number 2, or rule number 3 not supporting rule number 2, or rule number 2 not supporting rule number 3. So the inference engine must determine which rule to fire from such a set. So you have two conditions met. Traffic light is red. Which rule should I fire? Because if I fire the first one, I will stop. But if I fire the third rule, I will go. Right. So again, imagine a car that's programmed for such a thing. You have a camera in front of the car, and then your car sees a traffic light, red or green. Then what should I do? So a method for choosing a rule to fire when more than one rule can be fired in a given cycle is called conflict resolution. You have these two rules which seem to go against each other. So which rule should fire first? Or which rule should fire and the other one shouldn't fire? That's called a new area called conflict resolution. Now in forward chaining, unfortunately, both rules would be fired. Rule 2 is fired first, right? Because remember we said before, you process it vertically. So you process it vertically, that means that rule 2 is fired first because it's the topmost one, and as a result, its then part is executed, and the linguistic object action called value, the value called stop will stop. So imagine if you program this to a car, an autonomous car, based on your sensor, which is your camera, right, to look at the traffic light. Now, when it comes to the next rule to execute, right? So imagine this is actually in your PC or some sort of processor, very fast. So after first rule number 3, it could jumps to rule number 3. It will then process rule number 3. Now, rule 3 is also fired because the condition part of this rule matches the fact traffic light is red, which is still in your database. As a consequence, the object will then go. So it will override the first one. Instead of stopping, it will go, right? Split second, especially if you're looking at a fast processor, it will process it and it will get the car or vehicle to go. So how do we resolve those issues? Now, this one, one of the, of course, there are many ways as usual. The first way to do it will be you fire the rule with the highest priority. Right? So in simple applications, some of the simpler applications, the priority can be established by placing the rules in an appropriate order in your knowledge base. Now you can see you have to place the rules. So in this case, if I believe that rule number 2 has a higher priority, right? I will put it at a higher priority in my other list. As a higher means it's a. I think basically I've seen before some of these other work. For example, if your action of your rules affects human safety, right? That has a higher priority if it doesn't affect human safety. When human safety is at stake, I will put that as a higher priority, higher importance. Okay. So now this one works very well. As far as I said here, it works very well for the simple applications. That is, when you have less than 100 rules, 100 or less rules, right? This one works very well because it's quite easy to have a list, a priority list, right? Put them in a certain order in terms of priority importance. Then there's another method which is actually you fire the most specific rule. There's something called a specific rule, the most specific rule. Now this one is also known as the longest matching strategy. It's based on the assumption that a specific rule processes more information than a general one. So this one is actually, I think this one is not obvious in our earlier example of the traffic light, but there will be other examples, other cases whereby this one will be very clear. Maybe I'll go back and look at it and try to give you more examples on this. So this one, I think basically what it says that if your rule has more information, right? So I'm just thinking now in such a situation when the traffic light is like a green or red or whatever, is there something else I can also add on? So actually give you more information for that rule, right? So maybe for example, I add in more information. For example, if the traffic light is red, and there are no person on the road, right? Or if the person on the road, then your rule number 3 will have a higher priority, right? Because now if I add the now my rule number 3 has changed now to have more information, right? So this is more specific, right? So and also maybe for example the time of the day, middle of the night or 2 a.m. in the morning, there's less people, then maybe that one has can have a still can go. Right? Again, it's basically saying that you if the rule has more information, right? So it's more specific. And then the third one is the third method is fire the data most recently added into your database. So this is actually based on the liveness, real-time condition of your database. Now, so what does that mean? It means that you have to now provide a time tagging to the data that's attached to each fact in the database. So when is that information added to your knowledge to your database, not the knowledge base, database? So you will then look at the time tag. So what happens then? In the conflict set, the expert system will then fire the rule whose antecedent, the if part, uses the data most recently added to the database. So you have to base it on the most recent information. So because now most recent means that you have to find the time tag, the tagging, the time when this piece of data is actually active into your database, from the database. I think now, okay, now there's a question here. Chung-Yi, good comment. So Chung-Yi is saying that maybe traffic light opposite direction lights up. Again, I think you can see because I think this is a simple example. Of course, you can also put in more information. I'm assuming that your camera only is pointing at the set of traffic lights pointed at you. You're not looking at the one in the different direction, right? Because I'm looking at basically autonomous car, a vehicle that drives by itself. So I assume that your camera will only look for the traffic light that is pointed at your car. That means that you are not looking at. Of course, if you say that I know my camera looks at all traffic lights. So imagine at the intersection where I can have more than one set, whereby, like you said, in the opposite direction, right? So again, the opposite direction say stop, but actually your side no, opposite say green, your side say red, right? So you can also have all these various combination. So you can see, of course, the logical thing will be your camera should be pointed only at the traffic lights in the right direction, or just pointed at your car. You shouldn't be looking at other traffic lights. Of course, that by itself is another problem. In a busy intersection, how can you get your camera to look at the right set of traffic lights, right? Of course, it's not difficult, but of course, it's also it is a challenge by itself, right? So you have to figure out how should you look for your cameras, and of course, at other places, I can also think of your traffic lights itself. I know in certain places, you have two sets of traffic lights pointed at you. One says that you can turn left, one says you can go straight. But what happens if the traffic light, the one can say turn right is red, and the one going straight is green? So which one should I follow? So these are things you have to again. These are things that you only face it when you need to design such a system. So it's not so straightforward, right? So of course there are more things to do. Now we look for another one. Something we call meta knowledge. What is meta knowledge? Meta knowledge can be simply defined as knowledge about knowledge, right? So it's actually information to describe about information. Simple way of looking at it. So meta knowledge is knowledge about the use and control of the domain knowledge in the expert system. So it tells you when to use it and how you control such knowledge in the expert system. Now, in such a rule-based expert system, meta knowledge is represented by, surprise, surprise, meta rules, right? Again, what's a meta rule? A meta rule will then will tell you the strategy for the use of past specific rules in the expert system. Now, this is the bottom part here is actually I've added in. I think I've added in. So because I find that in the past, some students have difficulty understanding what you mean by knowledge, meta knowledge. So basically, meta knowledge is a piece of data that describes the knowledge in the world of AI. It is not specific to any single domain, but aims to describe the structure of the data present in the knowledge systems. Now, when you use it, the main usage of meta-knowledge is to understand and improve the nature of your user interface components and to maintain the knowledge base that are used alongside inference engines as well. So this one actually talks about providing you more information when you use such rules in your knowledge base. It's not about your database, it's about your knowledge base. So like for example, what Chunyi talked about, you can describe how you use the rule. If the traffic light is red, right? Maybe I can also put in more things. If the traffic light is red or green, right? Check for other things. So this will give you, if there's a conflict now, this other information will actually avoid such conflicts, especially if you can put in the right information, right? As I said, maybe one way is actually if there's a conflict, how can we resolve this? If the traffic light is red and traffic light is green, green one say you can go, and the red one say you can also go, right? So, right, that's what we say, isn't it? Here, right? Red light is okay, here, red and red. Oh, okay, good. Let me see. I think they stopped. Otherwise, I was hoping that I could print all this, but looks like I cannot. So we take a short break and then we come back. Okay. Now again, those of you if you have questions, please feel free to ask me. I'll be happy to answer some of the questions if you have any. The rest of you take a short break and we come back. Say 5 minutes. All right. In the new norm now, I don't think you need to go very far. Like the old days, if you are in the, I think our lecture is in the, I think in the DKZ, I think, for one of the DKs because there's 90 students. It's a large class. So in this case, I think it will be a short break. Say 5 minutes and we come back. Meanwhile, any questions? Okay, no, I'll also get myself a drink. I'll see you back in 5 minutes time. Thank you. Okay. Can I continue? I think should be fine, isn't it? Can hear me? Huh? Any questions so far? Good. See, let's continue. So we are talking about the meta knowledge, and then the meta knowledge is again, if you take away the meta, the word meta actually is the same concept. So previously we know that knowledge is represented as rules. So clearly, logically, meta knowledge will be represented as meta rules. Now, what's the first meta rule? Number one. So this one actually you can see here. Actually, this in a way will allow the system to actually process, especially in the case when the knowledge, the knowledge base contain rules which seem to be in conflict, right? So this will tell you now, if you have rules supplied not by experts have a higher priorities than rules supplied by novices. What do you mean by that? So novices will be people who are actually not so expert. If I can explain it in a very simple way, of course they will experts, and then there'll be someone say, if you say, ask so and so, what should I do in such a, okay, maybe for example, going back to our example about the weather forecast. So if your rule consists, if your knowledge consists of rules supplied by me, for example, I'm not expert in weather forecasting. I said today it will not rain. So that rule that you asked me would have a lower priority compared to if you talk to a weatherman expert who has maybe 20 years working forecasting the weather. So that is a simple way of explaining this meta rule number one. Now, meta rule number two, this is very important. As I think I also hinted at this early on. The rules governing the rescue of human lives or maybe safety of humans have higher priorities than rules concerned with clearing overloads on power system equipment, for example. So if your rules involve the safety of humans, of course you have to be more careful, higher priority. Rescue means you rescue humans. Then if your rules just to say clear overload, now what should I do? Our power system equipment. So basically, you can see here is that meta rule basically describe how other rules should be used. So in a way, it tells you, especially, it will be very useful when you have especially conflicts of the rules. What are the advantages of the rule-based expert system? Now, I think we're coming to the end of this topic. Now, clearly you can see, I think as some of you pointed out, it's a very natural way of knowledge representation. Because here you look at it, an expert usually explains the problem-solving procedure with such expressions as this. In such and such a situation, I do so and so. I do such and such. I do this. So if you talk to expert, interview an expert, right? So these are the things that you can capture the expert's knowledge into this sort of rules. Because the mechanic told me that if my car cannot start, I should check for my, first of all, check for my petrol tank. Then I check for my fuel tank, battery, is it flat? So this one is something that if you reflect back, that is something you actually do without even knowing it, right? We do this, right? So this expression can be represented quite naturally as a if-then set of production rules for your expert system. Secondly, the advantage of a rule-based expert system is that it has a uniform structure. Now, such production rules have a uniform if-then structure. I think some of you pointed out before. It's so common to all of us. So I mean, I'm surprised that somebody may even get bored. So surprised with such learn such things. Now, each rule is an independent piece of knowledge. So the rules will capture each set of rules. Each rule by itself will capture one piece of information or knowledge about that subject. Right? It's because of this uniform structure. Right? It's actually because of this very syntax, the way such information, such knowledge is represented. Right? So it's a very syntax of such protection rules and enables them to be self-documented. So you can look at the rule and you can say, that's why the system tell me that I should not bring an umbrella today because it will not rain because of these rules. The rules itself is actually for us to easily understand, right? Why you tell me to do such a thing, right? So these are things that these are the advantages of your rule-based expert system. Furthermore, I think this is something we also talked about before, that there's a separation of the knowledge. That is the what do you call it? The knowledge base, which is the set of knowledge, the rules itself, is separated from its processing. The structure of a rule-based expert system provides an effective separation of the knowledge base from the inference engine. So the inference engine is the one that processes all the knowledge base, the rules themselves, as separated, right? So this makes it possible to develop different applications using the same expert shell system. System shell. That means that you can use the same inference engine, but the rule-based knowledge base can change, right? Again, you still so if you use the same processing can use it for other different applications. The other thing is that I think we also talked about this before, that it can deal with incomplete and uncertain knowledge. The information is not complete, right? And also sometimes it's not so clear or uncertain. So the most rule-based expert systems are capable of representing and reasoning with incomplete and uncertain knowledge. Again, this is something we actually compared before with your computer programs, right? So you would need to detect the inputs from the sensor. If the information is not complete, your system will crash, will not be able to do its work. Then what are the disadvantages of your rule-based expert system? This is the first one is there's opaque relations between the rules. What does it mean? It means that although the individual production rules are relatively simple and self-documented, their logical interactions with the large set of rules may not be clear, opaque. That means that the rules, how is rule number one? I think go back to our earlier conflict set of rules. If the traffic light is red, you stop. If the traffic light is green, you stop. How are they interrelated? It's not very evident, not very clear. Rule-based systems make it difficult to observe how individual rules serve the overall strategy. Right, you add rules to it, there's a whole set of rules, but it's not clear why I need those rules, especially when you're developing a large system. So you also hinted at what? You may have more rules than necessary, so may not be efficient. Right? I use the word hinted. Because you just add the rules. So the rules are useful or not may not be very clear, right? So how does each of these rules serve the overall strategy, unless you're clear on that? There's also now come to this ineffective search strategy. How do you search through the rules? The inference engine, the one that processes the knowledge base, right, applies an exhaustive search through all the production rules during each cycle, right? The key here is exhaustive search. It means you need to go through all the rules to come to a conclusion. Now, expert system with a large set of rules, that is more than 100 rules, can be slow, obviously, and therefore the large rule-based system can be unsuitable for real-time applications. Of course, you can say that it may not be clear to you, but you can imagine if I want to have a split second reaction to the condition, to the situation, and it takes maybe 1 second to process. Right, 1 second may not be large, but 1 second can be quite significant. What do I mean by that? A couple of years ago, I have one student. We actually wanted to look at. I think some of you are doing that with Dr. Go Coming to identify the potholes and the stop in time, something on the road for you to stop. I think you can also think of it as your autonomous system, autonomous vehicle. That means that if I see something in front of me, right, I should stop the car, especially if it's a human, right, walking, crossing the road, right, I should slow down or at least I should stop. Now, we actually calculated if you're traveling at a certain speed, right, how long does it need you to stop to decelerate from here to there, right? If you see something that means I need to be able to see, say within a certain distance for me to determine, and that distance actually is very dependent on your speed. The faster you go, you need to be able to locate, identify the object in a further distance because you need to slow down. So 1 second is not a lot. Imagine if you're traveling normally 60 kilometers an hour or 80 kilometers an hour. How long does it need to recognize the object in front? So if you're traveling at that speed, you find that you need to have a very further distance, right? Because at that speed, you need to slow down. So if at that longer distance, if you're traveling at higher speed, the object can be very small. So this was what we did in I think 2-3 years ago as a FIP. We want to look at. I think we're not looking at humans. We're looking at the potholes for us to adjust our what I call that our suspension, right? Because if you have a pothole, I want to have a stronger what I call stronger suspension because I will be rolling over that pothole, right? If there's no pothole, I'm okay. So we actually found out that in the earlier FIP. Moving along, we have this disadvantage of the rule-based expert system is not able to learn, inability to learn. Now, in general, your rule-based expert system do not have an ability to learn from experience. It doesn't, you cannot learn from experience. Unlike a human expert who knows when to break the rules, this one basically is, I thought as you can see, actually open inverted commas. An expert system cannot automatically modify its knowledge base, the set of rules, or adjust existing rules or add new ones. You cannot do any of these three. Yes, you can still do it, but you need the knowledge engineer for revising and maintaining the system, to change the rules, to adjust the rules, right? To modify the rules or add in new rules, or even to eliminate, like in the earlier case, when the rules obviously are wrong. There's a conflict. If there's a conflict, unless it's necessary, you will need to remove it. Okay, so not too bad. We have finished. We come to the end now. So recapping, what have we learned in this topic, expert systems? We talk about what is knowledge. That's where we started from, right? Because at the end of the day, what we wanted to do is to replicate, to have another expert, which doesn't need to sleep, doesn't need to eat, right? Can work 24 hours a day without complaining. So how to represent the expert's knowledge? So first of all, in order to able to represent knowledge, we need to know how do we define knowledge? What is knowledge? So we actually spent some time to look at what is knowledge. Then we found out that knowledge can be represented by a set of rules. So rules as a knowledge representation technique, right? If then, else, or if this and this, if this or this, as a set of rules. The rules have two parts, main parts, which is the first part is known as the antecedent part, right? And then the next part is then the consequent or the action part. Then we look at if you were to develop such an expert system, who are the main players? Who do you need to to be inside the team, inside the development team. We found out there are actually 5 main players: the expert, which you actually get the knowledge, the project manager, the knowledge engineer, and then you have your programmer, and finally, of course, you also need to be aware what your customer or your user needs. Otherwise, you're developing something that the user doesn't want, or the user wants, but something you didn't develop, even worse. Then we spend some time to look at the structure of your rule-based expert system, right? So what is the structure of your rule-based expert system? And we look at some of the main characteristics of an expert system. Before we look at the 2 main methods of the inference engine, how does the inference engine works? We look at 2 methods, which is forward chaining and your backward chaining. Forward chaining is data-driven, whereas the backward chaining is maybe objective-driven, or goal-driven. I think that's the correct word, goal-driven for your backward chaining. We also found that in some cases, you can also have wrong rules being injected or included in your knowledge base. So the rules actually created conflicts. But in our example, it's very clear the rules shouldn't be there. If the traffic light is red, you shouldn't be going. You should stop, right? Unless there's some reason. So in such a case, obviously it is an error. So this one needs to be removed. But having said that, it's also sometimes not easy, because why? Especially if you're not the initial developer, you're just taking over from someone else. Imagine your senior developed such a system, expert system, in the past 2 years. So he has actually finished his FIP, has gone on, no longer contactable, or don't want to be contacted. And he has actually had 1,000 rules there. Imagine you have to go through all the 1,000 rules to actually find the bug. So that can be quite tedious. And then also you'll be figuring out why he put that rule inside, right? Because you cannot simply delete unless you know why, what was the reason why the rule was included in the first case, right? If you simply delete, it might create more problems than good. So that is what we call conflict resolution. And then we find that there are some ways to actually resolve such conflicts by setting certain priorities to the rules. And then there's also where we learn about meta knowledge, and then how we can use the meta rules to describe meta knowledge. That's one of the things is that, for example, if the rules involve human safety, so you have to be more careful to have a higher priority to such rules, so that those rules will affect, right? So I think, for example, one of them would be, if back to our example of the red light and of the traffic lights. So I would say that if the action is go, I will have that as a higher priority, in the sense that, no, the other way around. If the action is stop, I would then have a higher priority. It's better to have the system stop rather than go. So if there are 2 rules there, I will probably give a priority of, say, 1 to 10. 10 is the highest priority. I will say stop is the highest priority. I'll give it a 9. Traffic light is red, I will stop. 9. 9. Then the other one is actually traffic light is red, I will go. I will give it maybe only 2 or 3. So that if you compare the 2, the system will then get the system to stop, because it's safer, right? So you can see that. Oh, okay, that's it. Any questions before we stop here? We stop here, as in I will start the next lecture, the next topic. There's a question here from Chung Yi. Would global temperature, local temperature considered as meta knowledge? Again, Chung Yi, I cannot answer you that, because it depends on the application. What are you looking for? What's the application? I can see. I think you can see, as an engineer, scientist, you cannot seem to give an answer. Yes, no. Can you explain further? What do you mean by, what is the application? Oh, climate monitoring. So what's the output of your system? Because you see, I'm trying to understand that, because global knowledge, global temperature, what is because if your application is more towards Malaysia, why would I care about global temperature? right? So okay, maybe there is one example. Yeah, you can say that. You can say that. Maybe again, I'm no expert here, but I will just give you my guess only. Yeah. So I would be a bit. I will not be able. How should I put it? I do not really know, because if I say it's so the end of the day, if it's so I think what the Chun is trying to say is that if I have information, if I have if temperature is something something, then there is uh, climate change. So if the global trend is, if that temperature is based on a global trend, I will have a higher priority, right? Because maybe that is still possible. But then again, you know, but I'm trying to see if I am only doing this system for Malaysia. If my data is actually on the global temperature, right? But if I have higher importance on the global temperature, would that create an accurate system for Malaysia? You see, that's where I'm coming from. Because at the end of the day, your accuracy of your system still depend on whether your output is accurate for the user, right? If your temperature is based on, for example, how should I put it? Say Western countries where the area is temperate, you find that if that is true, you have 4 seasons. You can even go below 25 degrees. Malaysia, you cannot go below 25 degrees. Our temperature is actually only changes within a narrow band. 25 maybe. I think at some point you have 24, 25, and then at night, then you have also maximums of 33 degrees maybe. But in the other countries, I can go to 0 degrees, right? So again, I'll be a bit cautious, right, to use that methodology. Of course, but it gives you additional information about the information. Information. That's one way to put it, right? So if I may say that. Okay, let me shut this down and then I'll start a new topic. So any questions so far? Okay, let me set up the next part. The next, I'll start a little bit before we stop. So any questions? Let me check. Let me check. Let me pull up the next lecture. The next lecture will be, I think this one will be extension of what we're doing so far, what we're learning so far. This is the uncertainty management. Okay, let me make it easier. Stop the recording and then open up a new one. Okay, any questions? I know that some of you are very shy on. Don't want to get yourself recorded. Any questions? No? Okay, we'll start again. Now we can put up your next topic, topic number 4. Okay, I got it. So you can see the screen, the new. So let's move on to a new topic called uncertainty management. This is an extension of your expert system and also a rule-based system. As usual, this is what we hope to learn at the end of this topic. Probably we can finish it by tomorrow. So what is uncertainty? Again, because the topic itself is based on uncertainty management. How do we manage uncertainty? Right? So I can clearly see every time we do something, we have to go back to the basics. If we're doing uncertainty management, how do we define uncertainty? So we know that, again, it's about scoping. Again, in the earlier case, if you're doing a knowledge management system, a knowledge expert system, which is based on knowledge, so we need to be clear. What you mean by knowledge and how can we measure knowledge? So in this case, if you're doing uncertainty management, first of all, we need to figure out what you mean by uncertainty. Then we will spend some time to revisit your basic probability theory. And then we will then spend some time to look at the one method to handle such uncertainty management, uncertainty cases, uncertainty events, uncertain events, which is using what we call the method of Bayesian reasoning. Now, Bayesian reasoning, although it is useful and powerful and well used, common, popular, however, the Bayesian method has some biasness. It will bias towards certain things. So we look at what you mean by that. What are the biasness of your Bayesian method? Now, while Bayesian method is popular and is widely used in your reasoning system or for your expert systems, obviously it has a certain limitation and certain weaknesses. So we want to look at an alternative method, which is overcome some of those criticism of your Bayesian method, which is your certainty factors theory, and also evidential reasoning based on evidence, right? So to actually overcome some of those weaknesses of your Bayesian method. For those of you who are keen to explore, I believe that there is a Bayesian toolbox in your MATLAB. You can also pull up that part, and actually it's quite useful and also it's simple because I think one of the beauty about the MATLAB is that you can only just use 1 or 2 lines of code to actually run that to actually create that Bayesian method. Unlike the old days, we had to program everything from scratch. So let's look at what you mean by uncertainty. What is uncertainty? Right? So again, we go back to the basics. Uncertainty is based on information, right? Information as a result because information can be incomplete, inconsistent, right? Again, I think we've seen before, the information is inconsistent, right? Sometimes they say this, sometimes they say that. Uncertain or all three, either one of them or all three together complete. So it's actually even worse, incomplete, inconsistent. The one that you have is actually incomplete. So one you have is inconsistent and also uncertain for all three. So as a result, the criticism is that information is often unsuitable for solving a problem because of that. So if you look at it, uncertainty is defined, right? Again, I think nowadays you don't have to worry about that because especially when you're doing an open book test exam, you can actually find out if you were asked about uncertainty. But again, I think such information when you actually test your, basically, I am not a great fan of such things, such questions, because if I ask you define uncertainty, basically you're testing my memory. How good is my memory, right? To remember what's the definition for uncertainty, right? So uncertainty is defined as a lack of exact knowledge, right? So it's not about knowledge; it's exact knowledge that would enable us to reach a perfectly reliable conclusion. Because your knowledge is not complete, not exact, therefore I'm not able to give you an accurate conclusion, right? So yeah, I think going back to our example again about the whether today will rain or not, whether today it will rain because it's so hot for the past few days. So it's based on, if the information is not complete, not exact, I will not be able to tell you exactly whether it will rain or not, right? In the classical way of looking at knowledge, so classical logic permits only exact reasoning. That's the old way of doing things, a classical way of doing things, logical reasoning. But unless you're able to give me exact knowledge, otherwise I cannot give you the output of reasoning. So it assumes that perfect knowledge, the classical way, assumes that perfect knowledge always exists. So the law of the excluded middle can always be applied. So for example, if A is true, then A is not false, right? So it's actually, this is your classical logic. So okay, A is true, then A is not false. Now A is false, then A is not true. Okay, you can see that. So this is the law of the excluded knowledge, excluded middle. Is the third of the three classical laws of thought. This is actually based on I think the philosophy of thinking. So it basically states that for any proposition, if A is true, for example, this proposition, either that proposition is true or its negation is true, which is here, negation is true. So you can see here, if A is true, of course, I can say A is true, right? So nothing much, but the negation of this, A is true, then A is not false. So actually, it's a negation of this. It's also true. Right? So you can see, actually, can be quite. Jinhui, you have a question. What is it? Let is it? Is it? Let me see. I go back. I need to check with you. Is it 1ET or IET or LET? Jinhui. Typo. Okay. Where is it? Typo there, is it? Let me check back. In the slides, is it? Okay, let me check. Where is it? LET, IT. No typo, is it? Oh, okay. Okay. So you okay? You're fine. Can I continue? Okay. Okay. Sorry. I miss you. I sorry. Always communication. Sorry about that. So where are we? Okay. Talk about this law of excluded middle. Now we talk about definition of the uncertainty, right? So we talk about uncertainty is based on, basically, is a inexact knowledge. So what do you mean by, where are the sources? Where do you find such uncertain knowledge? For first thing is with implications. So your domain experts and your knowledge engineers, remember your team members in your team. Your team members in the team, which is the knowledge engineer, will talk to the domain expert to extract the rules by talking or interviewing the domain experts. Now, domain experts and knowledge engineers have the painful task, right? It's troublesome, of establishing concrete correlations between the if condition part and the then part of the rules. So by interviewing your domain expert, you will then able to generate your rules. So it's not easy. So that's why they say it's painful. So therefore, your expert systems need to have the ability to handle weight associations, not very strong, right? It's not very strong. the association between the if part and the then part. For example, by now accepting the degree of correlation as a numerical certainty factor. So remember I asked you before, early on, if the sky is blue, no clouds, or no clouds, and the weather forecast is no rain, then I do not need to bring umbrella. So I asked you before, what is that probability? It is 100%. There's no certainty factor. There's no probability attached to that. It's always one. Back to your Boolean logic. It's always one. But now we're seeing that there's a degree of correlation now. There's a certainty factor, which we will explain more in the next few slides. So based on, this is one part. Then our second thing is also based on the imprecise language, the language of the language itself that we use. It's because our natural language, whether it is Chinese or English or Malay, I suppose, is actually can sometimes be ambiguous and imprecise. We describe facts with such terms as often and sometimes, frequently and hardly ever. Hardly ever means the same thing. So we are always at this time of the year, it hardly rains. Hardly means that we think that it will, most of the time it won't rain, but still possible that it will rain, right? As a result of this ambiguity and impreciseness, it can be difficult to express knowledge in the precise form of the if-then form of the production rules. Because of this ambiguity, right, and the impreciseness, we cannot then form the if-then rules. Now, however, if the meaning of the facts is quantified, right, if the meaning of the fact can be quantified, then it can be used in the expert system. So in 1944, Ray Simpson did a study involving 355 high school and college students to place 20 terms like often on a scale between 1 and 100. Then 34 years later, this Milton Hackle repeated this experiment. Okay, and then you can see the results. I think I will not be able to explain in sufficient detail for you to understand if I will to carry on. It will exceed 12 o'clock. So I think I'll stop here and continue tomorrow morning at 9 o'clock. Is that okay? Okay, we will stop here. Again, as usual, before we stop, any questions for me that you want to comment or questions, right? Otherwise, you all can go for your lunch. And I'll see you tomorrow morning at 9 o'clock. Okay. Otherwise, bye-bye and see you tomorrow morning.